In this screencast, we're going to focus on finding the tangential and normal components of acceleration. The goal is to take the acceleration vector, so for example if we're in projectile motion, and break the acceleration vector up into two parts. I can calculate the tangential vector, which means there's a line upon which I can project the acceleration, and the acceleration can be projected into two parts. You have the tangential part and the normal part. This vector right here is our part in the tangential direction. It's an amount in the tangential direction, and then we're going to add to it the amount in the normal direction. Our job, find a sub t and a sub n. One way to do that is we can just use exactly what we said, that a sub t should be the projection of a onto t, and using the projection formula, that's a dot t over the magnitude of t times by t over the magnitude of t. But since t is a unit vector, then what we find is that this number right here is a sub t. Similarly, a sub n is take a and dot it with n. If you have t and you have n, that's exactly how you can find those components. All this is it's writing a vector a as a vector parallel to t plus a vector orthogonal to t, something we did back in the vectors unit. There is another way to look at this which actually sheds some light on centripetal acceleration. To get that, what we're going to do is we're going to take a, and we're going to write it as the derivative of velocity. Well, velocity can be written as its magnitude times its direction, which means acceleration is the derivative with respect to time of speed times the unit tangent vector. This is a product, a scalar product. That's a scalar, a number, and this is our vector. And since it's a product, it obeys the product rule. I'm going to take the derivative of the first times the second plus the first times the derivative of the second. This was the product rule. Once I've used the product rule, this first part actually is the amount in the tangential direction. We need to now understand what is dt dt. To do that, recall that dt dt showed up when we were calculating curvature. Curvature is dt ds, which means it's dt dt over ds dt. Well, that means that curvature is t prime over speed. I guess speed we can write as the magnitude of velocity. So t prime is the curvature vector times speed. I'm going to take this and put it up there. So I get the derivative with respect to time of speed times the unit tangent vector plus speed times the curvature vector. Now I'm going to repeat what I did up here with velocity for the curvature vector. The curvature vector can be written as its magnitude, the curvature, times the vector, unit vector in that direction, which is n. So this last part right here is really speed squared times kappa times n. This number is a sub n, and this number is a sub t. Now let's do some applications and explain who cares. Why did we do this? If we look up here, as you are rising in projectile motion, when you're at this point, as you're rising, your speed is slowing down. The vector points opposite the direction of motion, which means that the component at should be negative. Well, if this number right here is negative, then that means the rate of change of speed is negative, which means you are slowing down. That's why at this point you're slowing down. Whereas opposed to this point over here, if you're at this spot, then gravity's pulling you down and you're getting faster and faster, which means that your rate of change of speed is positive, which means that the component of the acceleration in the tangential direction should be positive, which is precisely what happens. Now, over here, to understand how the normal acceleration works, we're going to imagine for a moment that you're driving on a road and there's a switchback on it. So you're going up a mountain pass and you're hitting some switchbacks. As you're driving down the road here, maybe you'll see a sign that says you can go 45 miles per hour. When you get near the corner, you're going to see a little sign that has a U-turn symbol on it. And then underneath it, it'll probably have something like go 15. Why in the world do they tell you to drop your speed? Well, there's an acceleration pulling you in the normal direction. If that acceleration gets too big, your tires may lose friction on the road and you could fly off the road. So the goal is, let's try and keep you from flying off the road by reducing the acceleration in the normal direction. Well, the acceleration in the normal direction is the speed squared times the curvature. If I take my speed from 45 down to 15, then I have 1/3 the speed. But if I take that third and square it, I get a 9th, which means by reducing my speed by a third, I 1/9 the normal acceleration. I could instead just say, let's dig into the mountain more and try and make the curve not as sharp. But if I half the curvature, I only half the normal acceleration. Whereas if I half the speed, I fourth the normal acceleration. Changes in speed greatly affect the acceleration in the normal direction, a whole lot more than changes in curvature. That's why this equation happens to be important.